Exercise 1, evaluate the double integral. So these are supposed to be like nested in one another, like this. If you see two integrals and then like something like dy dx on the end, what that's saying is I'm taking an integral of all of the stuff that's happening inside and so we deal with the orange part first. We're going to work our way from inside out. And when I do the orange part, I am just taking the antiderivative with respect to y and not with respect to x. So we pretend that x is a constant, just like we did when we were doing partial derivatives. Whenever we would take the partial derivative with respect to y, we would pretend that x was a constant. Now when I take the antiderivative with respect to y, I'm going to pretend that x is a constant. So like my antiderivative of 2xy with respect to y would be x times y squared. What's the antiderivative of 3y squared? Y cubed. And then we had lower bound 1, upper bound x. Whenever I plug in the upper bound and lower bound into this expression, I'm only going to plug that in for y. So in other words, this is going to be x cubed plus x cubed minus x plus 1. Again, since that orange integral in the middle was integrating with respect to y, then whenever I plug in the upper bound and lower bound of that integral, I only replace the y variable with the upper bound and lower bound. I do not mess with or replace the x variable. Okay, and then we're ready to do the next layer, which is the integral from 1 to 2 of 2x cubed minus x minus 1. And this is the antiderivative with respect to x, and so I get 1 half x to the 4th power minus 1 half x squared minus x from 1 to 2. And then you plug in your 2's. And then you subtract and plug in your 1's. And we get something like 8 minus 2 minus 2 minus a half plus 1. So those cancel. 8 minus 4 is 4 plus 1 is 5. All right, so hopefully there's nothing too crazy new here. You know how to do antiderivatives in Calculus 1 and Calculus 2. Ever since 7th grade, you learn antiderivatives. And then all you're doing is taking the antiderivative with respect to a particular variable, and you leave the other variable alone. Questions? Okay. Then we'll do another one for fun. First one was for teaching and learning. This one's just for fun. This one is the antiderivative, or the integral from 0 to 3 of integral from 0 to infinity of x squared divided by 1 plus y squared dy dx. So on the inside, in orange, you can see I'm taking the antiderivative with respect to y. So for the orange integral, we are pretending that the x is a constant. And so you probably remember this. I think I can take the x squared out of the orange integral, because as far as the orange integral is concerned, the x is a constant. And if I have a constant multiplier on the integrand, the inside of an integral, I can just take it out. But you can tell by where I put it, I cannot take the x squared out of the blue integral, because the blue integral is with respect to x. And so as far as the blue integral is concerned, x is not a constant. So I can only do something like that. What's the antiderivative of 1 over y squared plus 1? Okay, I hear a bunch of people whispering the right answer, which is arctangent of y. Then we take the antiderivative. We're going to plug in the upper bound and the lower bound. What is arctangent of plus infinity? Pi over 2. What is arctangent of 0? Very good. So we take pi over 2 outside of my integral because it's a constant. And then we take the antiderivative of x squared, which would be 1/3 x cubed. Plug in your 3, plug in your 0, and we get 1/3 times 3 cubed, which is 9, and then 0. So this is going to be 9 pi over 2. When it's all said and done. But you get the idea. You're taking an antiderivative for one variable at a time. And since the very first step, I was thinking to myself, all right, taking the antiderivative with respect to y, so the x's are like constants, and I can just ignore those right now. I can take the x's out of the inside orange integral because it's as if the x is a constant when I think about the orange inside integral there. Okay, questions? No? All right. This is kind of a silly question at first look, but I'll explain what we're doing. It says, find the area of the region shaded in the plane using a double integral. If you get this question wrong, I'm going to be really sad. I said, if you get this question wrong, I'm going to be really sad. It is 15. Very good. Now, what I would like you to do, and this is like overkill, right? This is like... I know. I don't know. I don't know what it's a good metaphor for this. It'd be like using your oven to warm up your Pop-Tarts in the morning, right? You should just use the toaster. It's faster, it's easier. But if you want to, you could preheat your oven, you could pop your Pop-Tarts in there, and you could heat them up that way. But it would be overkill. You're using the wrong tool for the job. But what we're going to do is we're going to say this area is going to be equal to a double integral of the number 1 with respect to y and with respect to x. And the lower bound of y is going to be 3, because that's the lower bound here. The upper bound of y is going to be 5. The lower bound of x is going to be 2, and the upper bound of x is going to be 8.
Should the lower bound of y be...
Oh, sorry, that's a 2. Sorry, my bad. Thank you. Here I am, like, if you don't get this answer right, I'm going to be so sad. And then I was prepared to tell you that this answer was going to be like 12. But, now we've got it. So my y variable is allowed to be anywhere between 2 and 5, and my x variable is allowed to be anything from 3 to 8 on those bounds. So you see the bounds of the integral matches the bounds of this region in the plane. And again, the inside integral goes together, right? So the last integral sign and the first d variable are connected. You don't read both from left to right. You read them in inside to out order. And so then what would it look like if I were to actually evaluate this? What would it look like if I say, I want this integral? So we would integrate from 3 to 8 with respect to x of this. What's the antiderivative of 1? Y. With lower bound 2, upper bound 5. And then we're going to plug in 5 and 2 there. So we get 5 minus 2. And 5 minus 2 is just 3. What's the antiderivative of 3? 3x. And so that's going to be 3 times 8 minus 3 times 3. Which finally gets us our answer that the area was 15. And that should agree with what you thought intuitively at the beginning, that that would be a rectangle with area 15, right? But the purpose of doing it this way, of writing it as a double integral and then working through every step, is just like a stepping stone for doing more interesting questions in the future. But I want you to start thinking about, how would I represent areas in the plane using the bounds of a double integral? Here's another one. Find the area of the shaded region in the plane using a double integral. And you know how to find this using a single integral. You did that back in Calculus 1 where this curve is y equals square root of x. But we are going to now set up an integral where my x values are allowed to be anywhere from 0 to 4. And for my y values, I'm letting the variable y go everywhere from 0 to the square root of x. If you said the bounds of your y variable went from 0 to 2, you would be wrong, because that would give you a rectangle, right? The top upper bound of y is not a constant. It depends on what value of x you have. So the upper bound of y needs to be a function of x. It needs to be that square root curve. So let's do this real quick. What's the antiderivative of 1? Y. And that's going to be from 0 to square root of x. And then we would plug in square root of x and plug in 0. And this is how you'd be familiar with working the problem from Calculus 1, is you would say, I'm going to take the integral from 0 to 4 of square root of x to get the area under the curve. And of course, the antiderivative of the square root would be x to the 3/2 power divided by 3/2, which you remember from 6th grade, that dividing by a fraction is the same thing as multiplying by the reciprocal. We could also multiply by 2/3, right? And then we plug in upper bound 4, lower bound 0. What's 4 to the 3/2 power? 8. And then we take our 8 and multiply it by 2, and we get 16/3. But the new part you're learning about is, how do I use the bounds of a double integral to represent an area in the xy plane? Okay. Oh yeah, I didn't finish this question. Where it says use both possible orders of integration, if I ever ask you to use both possible orders of integration, what I mean is you could say dy dx, or you could say dx dy. And so now let's work the same problem with the other order of integration. And so I want some integral where the outside integral is with respect to y, and the inside integral is with respect to x. So I'm reversing the order here. What should I make my lower and upper bound of y now at this point? 0 to 2, very good. And what should be my upper bound of x? Let's do the upper bound first. What's the upper bound of x? Carter's thinking about the lower bound, but I'm thinking about the upper bound right now. It's a lot easier of a question. The upper bound of x should be 4. Now, what's the lower bound of my x variable? This is the hard part. What is it, Alex? It's y squared.
Said Carter said the lower bound, and then we didn't just say Carter said the lower bound. I got confused. So it's just not what Carter said.
Okay. So what's happening here? I said over here, if I tell you that x can go from 0 to 4 and y can go from 0 to 2, that would be wrong because that would give me the whole rectangle. I don't want the whole rectangle. So we had to say that the upper bound of y was square root of x. But with this new order of integration, I need the outside integral to have constants as the lower bound and upper bound. Because when I'm done integrating, I want to have a constant number answer. I don't want to be left with any variables in my final answer. And if you think about it, if I made either the lower bound or the upper bound a variable or a function of a variable, then you'd be done integrating, you'd plug in the upper bound, lower bound, you'd subtract, and then your final answer would still have variables. So we don't want any variables in the bounds of the outside integral. So instead, I make the bounds of the outside integral constants. And in terms of just the constant numbers, y can go from 0 to 2. When I do that, x has a clear constant upper bound of 4, but the lower bound of x, what's the smallest x value I can pick? That has to be a function of y to capture this curve. And if you're trying to wonder, well, what function of y is that? Just solve this equation, square both sides of the red equation, and you get x equals y squared. So that'll do it. Now let's solve the purple and green integrals and see if we get the same answer, because we should get the same answer. If we don't, that's a problem. Antiderivative of 1 is x. And we're using upper bound 4, lower bound y squared. And so the integrand is 4 minus y squared. So what's the antiderivative of 4? 4y. What's the antiderivative of minus y squared? Yeah, here 1/3 y cubed. And then we plug in upper bound 2, lower bound 0. We don't really have to worry about lower bound 0 this time. Upper bound is going to give me 8 minus 1/3 of 8, which is 2/3 of 8, which is 16/3. So good. You definitely don't have to do this, but you could think about doing this with any problem on your next test. Like, what's one way I could check my answer, make sure I got the right answer? I could do both orders of integration. I could do dy dx and dx dy. See if I get the same answer either way. Anyways. Any questions? All right, this one says, exercise 3, sketch the region in the plane which the bounds of the integral enclose. So it's the same idea, but we're working backwards. Because in the last problem, I was giving you a picture of the region I wanted from the plane, and then you had to come up with the bounds of the integral. This time it's backwards. There's an integral, and I'm saying, well, look at the bounds, figure out what the region in the plane looks like. Well, when I look at this, I say x needs to be greater than -2 and less than +2. And y has to be greater than square root of 4 minus x squared and less than positive square root of 4 minus x squared. So if this is negative 2, and this is positive 2, I know that no matter what, the whole region is going to happen in between negative 2 and positive 2. As far as what that means for the y variable, though, we still haven't figured it out. When I look at this, and I see some like plus signs, some minus signs, I see square roots, I might think, what would happen if I squared every term in this orange inequality? Well, squaring is going to make every real number a positive number. And so on the left side, whenever I square the negative, it's going to be a positive. So I can just forget about the left side. And then on the right side, I've got a positive square root of blah, blah, blah. So let me say y squared needs to be less than 4 minus x squared. What if I add x squared to both sides? I heard somebody whisper circle. This is a circle with radius what? Radius 2, centered at the origin. And so what this is telling me is that the upper bound for y is this semicircle centered at the origin with radius 2. And look at the lower bound. Well, the lower bound is the same thing, but with a negative in front. So I'm allowed to get the same negative values of y. So that'll be the negative semicircle with radius 2, centered at the origin. So the region in the plane that the bounds of this integral are enclosing are inside this orange circle. It's this region. I would be integrating over this disk with radius 2. Does that sound good? So if I actually sit here and I do this integral, I'm going to get the answer 4 pi. Yeah, you got it. 4 pi, right? Because pi r squared is the area of a circle. And so that integral should give you 4 pi. So remember a long time ago when you took Calculus 1, your Calculus 1 teacher should have maybe spent 1, 2, 3 class periods talking about Riemann sums and the limit of what it looks like whenever you take a Riemann sum and you make the width of the rectangles go to 0 and the number of rectangles goes to infinity, and then it really closely approximates the area under the curve, and how that limit is the same thing as an integral, and that's called the fundamental theorem of calculus. Everybody nod your head? Yeah? Okay. So here's the idea. If I choose more and more rectangles in my Riemann sum, this gets closer and closer and closer to the actual area under the curve. And this is how we define the integral in calculus. Is they say, what is the limit as I increase the number of rectangles? That's the definition of the integral. And then we're not going to reteach the fundamental theorem of calculus because we don't have that much time on our hands. But when we had a single integral and that allowed us to find areas under a curve, now we're dealing with these double integrals. And if you want to know geometrically, what does a double integral tell me? It's like this. This is kind of like my Riemann sum. It's a double Riemann sum. And I can choose how many rectangles I want in the y direction and how many rectangles I want in the x direction. And that makes this nice grid of rectangular prisms. And I think these are midpoint rectangular prisms. So the very middle of each prism is set to match the surface. And that surface is obviously a function of two variables. So z equals a function of x and y. And in the limit, as the number of rectangles in the x direction and the number of rectangles in the y direction both go to infinity, and the width and the length of all the rectangular prisms go to 0, now I've got the volume of a solid that's bound between the surface and the xy plane. Okay, so that's what we're doing. If I ask to find the volume of a solid, then we're really just taking a double integral. So I could ask you, calculate the volume of the solid bounded by the surface and the xy plane inside the region R.
So does that mean that the circle we did was actually a sphere?
No.
No?
What?
So this is the area over which I'm taking the integral. If I had an integrand of 1, let's say, then what I just found is the volume of a cylinder with a height of 1 and that circle as the base. Right? But if I put some other function in the integrand, well, the circle is still the base of the solid, but now the top of the solid is defined by the surface that I put in the integrand. That's a good question. But like in this example, the base of the solid that we're about to talk about here, when I say calculate the volume of the solid, the base of the solid is a square. And the sides of the solid are going to be flat. But the top of the solid is going to be defined by this paraboloid. It's going to have like a rounded kind of top to it. We can look at this in GeoGebra maybe if it works. It's one of those things, I always say you have to have a really good imagination for this class because Dr. Maka does not draw. Here's my XYZ space. Here is my region R in the XY plane. So now I've got some paraboloid that starts at 2 and goes like this. But it's, a three-dimensional thing. This is a surface. And so the solid I'm talking about has flat sides and a rounded top that matches the surface of the paraboloid. A flat square base. Okay. Anyways, that's the volume we're finding. And to find this volume, we are going to set up a double integral over this region. By the way, dA means a small amount of area. And that could mean dx dy or dy dx. Right? Like x times y would give you an area. Dx means a little change in x. Dy means a little change in y. So a little change in x times a little change in y gives you a little packet of area. That's what I mean by dA. So you have to choose some order of integration, and it's up to you whether you want to do dy dx or dx dy. You can choose either one. And I'm trying to integrate 2 minus x squared minus y squared. And I have to decide what's going to be the lower and upper bounds of x. 0 to 1. And what's the lower and upper bound of y? 0 to 1. Yeah, that's pretty easy. Nice little square. And then we'll try to do this as quick as we can. So the antiderivative with respect to y is going to be 2y minus x squared y minus 1/3 y cubed. Plug in the 0, plug in the 1. And I don't really care about plugging in 0 for y, because that's going to zero everything out. What I do care about is what happens if I set y equal to 1. That's 2 minus x squared minus 1/3. Which will be 6/3 minus 5/3 x minus 1/3 x cubed. Plug in the 1, plug in the 0. Of course, the 0 doesn't matter, and we get 5/3 minus 1/3, which is 4/3. That's the volume of this weird shaped solid. It has a rounded paraboloid top and a square base. All right, let's try it in GeoGebra. Let's give it a shot. I'm giving it like a 10% chance of success. So that's supposed to be the top of my solid. The sides are trickier because the sides are going to be like y is equal to 1, y is equal to 0, x is equal to 1, x is equal to 0. And those are all the sides of my solid. And so when I say I had a 10% chance of success, I mean, I knew that GeoGebra could render this, but what I was really thinking about is like, does this help anybody? Like, can you actually see what the solid is? It would really be ideal if I could limit the domain in GeoGebra, like say I only want x to be from 0 to 1 and see what happens. No. Okay, see, that's what I was trying to restrict the domain so that I could just get the sides of the solid there. It's not in the cards for today.
Parabola, right?
Uh-huh.
Just built, but then your walls are your x and your y.
Exactly. This is telling you where the walls are of the solid. Yeah. Very good.
That helped a lot better. I thought we were starting the parabola with like squared edges, and I'm like, how is that possible? I did the double.
All right. Find the volume of the solid bounded by the paraboloid and the xy plane. And so this one would be really easy to visualize, at least. That's something we can actually do. It's 9 minus x squared minus 9y squared. Okay. So this is actually easy-ish to see. I only want the solid that's above the xy plane that would be bounded between the surface and the plane. So if you get a question like this, you should ask, what is the region R in the xy plane over which we want to integrate? Because there is an ellipse in the xy plane, and the entire solid is above that ellipse. And so we only really want to integrate this function above that ellipse. We don't want to accidentally extend the domain to be larger than that little region, otherwise it's going to mess up our integral. So let's try to capture exactly what that ellipse is in the plane. I want to know what is the base of the solid. And to answer this, remember the xy plane is where z is equal to 0. The xy plane is the plane where z is equal to 0. So I'm going to take my equation, set z equal to 0, and I get 0 equals 9 minus x squared minus 9y squared. Or I could write x squared plus 9y squared is equal to 9. And suppose if y is equal to 0, then x is equal to what? Yeah, 3 or negative 3. There's negative 3. Here's positive 3. And then let's solve for y. Y is going to be, oh sorry, I'm not drawing this right, because those are supposed to be negative and 3 for the x variable when y is equal to 0. So that should be here and here. Okay, then we solve for y. Y is going to be the plus or minus square root of 9 minus x squared divided by 9. Does that look good? And so that's going to give me the thing here. Let me think really closely about this. If x is equal to 0, oh, then y is equal to 1. So y is actually like right here. Okay, so the curve y equals square root of 1 minus x squared over 9 is going to give me this curve. And if I take the negative, it'll give me this curve. So here, now I'm ready to finally finish answering this problem. I want a double integral. And I want the double integral to be of 9 minus x squared minus 9y squared. Now I've got to choose some order of integration. It doesn't really matter, like dx dy, dy dx. For the lower bound of y, I need that lower bound to be negative square root of 1 minus x squared divided by 9. So I guess it does matter the order of integration, because I just found this for y as the lower bound of y. The upper bound of y would be positive square root of 1 minus x squared divided by 9. The lower bound of x could be negative 3, and the upper bound of x could be positive 3. And this is the double integral that will give me the volume of my solid. So the integrand is telling me about the surface. It's telling me, how do I find my z coordinates along my surface as a function of x and y? The lower and upper bounds of x and y are telling me what does the base of this solid look like in the xy plane. And it's important that the outside integral only has constant upper and lower bounds, because when I'm done integrating, I want to have a number for the volume that doesn't have any variables in it. But then that means for the inside integral, the lower and upper bounds of y have to be a function of x that actually describes what that curve is around my region in the xy plane. So, did that make sense? Hopefully. Yeah. Okay, exercise 5. Find the volume of the solid bounded between the paraboloid 1 minus x squared minus y squared and the plane z equals 1 minus y. And so this looks a lot like the previous problem. But this time the plane is not just the flat xy plane. The plane is not z equals 0. This time I've got a weird plane that's at a slant. It's z equals 1 minus y. So it's going to kind of slice the paraboloid at a diagonal. And so if I want the volume of that solid between that paraboloid and that kind of diagonal slice, we'll talk about how to do that too. First, let's find the x and y coordinates at the intersection of the paraboloid surface and the plane. Now, where they intersect, they have the same x coordinates, y coordinates, and z coordinates at the point of intersection. And so what I can do is just set z equal to z. In other words, set 1 minus x squared minus y squared equal to 1 minus y. You can subtract 1 from both sides. And it gives me something like x squared plus y squared is equal to y. And I can't find an easy way to solve this equation for y. I mean, I guess you could use the quadratic formula. But it would be easier to solve this equation for x. So let's just solve it for x and keep our lives as simple as possible. And so x is going to be plus or minus the square root of y minus y squared. Oh, I'm going to have to write both orders of integration anyways, apparently. So we're going to have to do it the easy way and the hard way. Anyways, this is going to be the places where these two plane and paraboloid surfaces intersect each other, is along these x and y coordinates that satisfy this relation. So what I'm going to do is set up the double integral, and for the lower and upper bound of x, the lower bound is going to be negative square root y minus y squared, and the upper bound is going to be positive square root y minus y squared. That's for x. The other integral has to be for y, and for the lower bound and upper bound of y, I just need constants, because I've already kind of characterized the relationship between x and y using these bounds. And now for the outside integral, I just need constants. So what's the lowest possible value of y that will still make it possible to satisfy this relationship with real number variables, like x is a real number, y is a real number? Well, what is the least value of y that I can use here? Can I use -1? Because it'd be -1 minus 1, right? It'd be the square root of -2. Oh, that gives me an imaginary x. Can I use 1? Y equals 1? That'd be 1 minus 1. That'd be 0. That's fine. I can take the square root of 0. So 1 is allowed as a y value. Is 0 allowed as a y value? Yeah. So 0 and 1 are allowed. What if I tried to use a number greater than 1? Is that a problem? Yes. Y cannot be greater than 1. And what if I tried to use a number less than 0? That would also be a problem. So y cannot be greater than 1, and y cannot be less than 0. Otherwise, my formula is not going to work. Now, we're almost done. What I need left is the integrand. What goes inside this double integral? Well, I should figure out what's going to be on top. Is the paraboloid going to be on top and the plane going to be on the bottom? Or is the plane going to be on top and the paraboloid going to be on the bottom? I can look at GeoGebra, but on a test, can you look at GeoGebra? No. So the reason why I want to figure out which is on top and which is on the bottom is because what I'm going to do is I'm going to take the one on top, the surface on the top, and subtract the surface on the bottom to give me the difference, and that will give me the volume. So the paraboloid is going to be on the top. Yeah. Well, what I'm thinking is a paraboloid can be face down or face up. I know this paraboloid is going to be kind of face down because I'm subtracting x squared and I'm subtracting y squared. So the maximum value of that paraboloid happens when x is 0 and y is 0. And everything else is going to be a smaller number. So this is kind of like a mountain-shaped thing. Yeah. So I think the paraboloid is going to be on top, and the cone is going to have to slice through it. And then I can make the integrand be 1 minus x squared minus y squared for the paraboloid minus the plane, which is 1 minus y. That is one order of integration. And now let's write the other order of integration that we're allowed to do, which would be dy dx. And when I write the other order of integration, I'm still going to have the same integrand. I'm still going to have the paraboloid on top and the plane on the bottom. This time, I need to find a way to represent the intersection between the plane and the paraboloid so that I get y as a function of x, because this time, for my outside blue integral, x needs to have a constant lower bound and constant upper bound, and the y variable, lower bound and upper bound, has to be a function of x in order to tell me where the curve happens. So let's go back to here. There's another way I could deal with this. I could rewrite this as y squared minus y plus x squared equals 0. And then we use the quadratic formula. That's y equals negative b, so negative 1, divided by 2 times a, plus or minus the square root of b squared minus 4 times a times c. Remember, x is a constant in a quadratic equation of y, and then divide by 2a, which is 2 times 1. In other words, I can write y equals 1/2 plus or minus the square root of 1 minus 4x squared divided by 2. That gets to be the upper and lower bound of y, because it tells me what y gets to be as a function of x. All right, now what do the constant upper and lower bound of x get to be? And remember, we're asking kind of the question, what's the smallest value of x where I can actually find a real value of y that satisfies this equation? And what if I had x equals 0? Does that work? Yeah, that'd be square root of 1, so that's fine. X can be equal to 0. What if I had x equal to 1? Does that work? No. 1 minus 4 is negative 3. That doesn't work. Basically, x squared can't be larger than 1/4. So x can't be larger than 1/2. And it can't be less than negative half. So my bounds on x are going from negative half to positive half. That's the only range of values where I can make this equation work and get a real value for y. So that is the same integral using two different orders of integration. Both of those will give you the volume of the solid bound between the paraboloid and the plane.
Did you try to solve these in a previous lecture? Is that why it says don't try to solve it?
Yeah. Well, so that's the note because I've taught Calculus 3 a few times, and we have like 75 minutes together to do this lecture. And so occasionally, especially when I was first teaching, I would just think, oh yeah, I'm going to solve this integral, why not? And then it would take me like 45 minutes, and it ruins valuable class time that we could have spent talking about other concepts, right? Really quick, if you want the average value of a function, divide by the area of the region. Okay? I'm not going to work this problem because we don't have enough time. But I do want you to know, if I want the average value of a function, take the double integral over the region and then just divide by the area of that region. Cool? And then the last one that I want to talk about is this one, because this one's super tricky. We're finding the volume of the solid bounded by the surface and the xy plane in the entire first quadrant. The entire first quadrant where x goes from 0 to infinity and y goes from 0 to infinity. And so the thing that we're trying to integrate is 1 over x plus 1 squared, y plus 1 squared. And I don't know if we'll have time to finish this problem, but I do want to tell you what's the correct way to think about this. And on the inside integral, I'm taking the antiderivative with respect to x. That means y is a constant as far as the orange integral is concerned. We can take out 1 divided by y plus 1 squared out of the orange integral. Now, if you have a situation like this where in orange the entire integrand only has x's, there are no y's in the orange integrand. And this is the other important part, the bounds of the inside integral also do not contain any y's. There's no mention of y the outside variable of integration anywhere in orange. I'm going to take the whole orange part outside of the blue integral because the entire orange part is just a constant as far as the blue integral is concerned. And you might even be smart enough to realize, hey, even though those look different, that's really the same integral. I'm just using a different symbol to represent my variable of integration. So we don't have time to finish the problem, but at least we've boiled it down to just a calculus 1 kind of problem where you do a single integral. I guess it's an improper integral, right? So this is a single calculus 2 type problem where you do a single integral with a single variable and then you square it to get your answer. Okay, that's it. Y'all have a good day.